Hello. This afternoon I'll be talking about High Integrity Agile and how we found application of these techniques in building safety and security critical systems. In particular, I've been looking, during some research I've been doing, at how we can combine the best of formal methods, lean engineering and the agile approaches in developing safety critical embedded systems. Some of the agile approaches seem highly appropriate for this domain, but some of them we're not so sure about and we have some concerns. Secondly, I'll be looking at opportunities offered by our experience with formal methods to improve the agile approach in the development of such systems. So I'm here to talk about some work I've been doing recently. To introduce myself, my name is Rob Chapman. I work for myself, run my own company, helping people build critical software mostly. Do some work with the University of York, which is my old educational establishment where I first graduated. It was very kind of them to ask me to go back, and I do a bit of teaching for them. I should also mention that this particular work that I'm going to tell you about what the hell do we do with Agile for building critical and embedded systems. This work is actually something I've been doing for Altran UK, the intelligence systems bit of Altran, which is based in Bath. Some of you may know it. The company that's always been in Bath. The challenge they really set me to sit down and have a big old think about this question: can we do high integrity agile? Does that even make sense? Is this a contradiction in three words? Well, we don't think so. The short answer is yes. So that's nice and simple. The long answer is, well, yeah, we think we can, but. And I could end my presentation there. You would be quite pleased if I did, maybe. But so what follows the but ... What are some of the issues? So I come from a background of 20 years of having built and thought about building critical, either safety critical or security critical embedded systems in military, in rail, defence, aerospace, nuclear, most of those kind of traditional regulated critical industries. So as an engineer used to that environment, if I read the Agile books or whatever, the Agile literature, what do I think? You know, where do I think, oh yeah, that's a great idea, we should do that? And where do I think, oh no, that will never work? And what can we do about those things? So that's what I'm going to talk about for the next 20 minutes or so, just to give you a sample, I suppose, of where we think some of the issues, but also some of the opportunities are. There are some areas where I read the Agile literature and think they've missed an enormous opportunity here. Some of the stuff that we normally do for safety critical systems, the Agile people just haven't realised and haven't woken up to. So there's a huge, what I would call a blind spot in the Agile community, where we think we already know how to do better than what they do. So okay, where are those things? I'll give you a little bit of background to some of the sources of material. As I said, we'll look at some of the assumptions and the issues that I've come across, but also the opportunities. The opportunities, what I would call turning the dials up, where I think the Agile community have missed a trick and missed out on some opportunity to do better. And I'll end with what the big question is. I know what the big question is. I'm not necessarily promising to tell you what the big answer is, unfortunately. So, by way of light reading, to give you, this is to really just give you an impression that I haven't made this all up. A lot of people have been thinking about this for a very long time. There's this impression that Agile, and more recently this stuff called continuous delivery and this stuff called DevOps, is all terribly new and fashionable. Well, actually, you can go back through the literature and find stuff like this. Felix Redmill, working at British Telecom in the mid-1980s, was doing something called evolutionary delivery, which if you read it and you think, oh, this sounds like Agile, hang on. And Felix had this worked out in the mid-1980s. He encountered a lot of the problems with it as well, which are reported on in papers like this from SafeComp in 1989. Going forward through the literature, there's a reasonable book by Barry Beam and Richard Turner. This is IEEE Computer, 2003. This is an interesting history. This goes back to things like the 1950s and 60s, talking about what they used to call incremental development, which was used on programs like the X-15, which was a rocket ship with a seat attached, and some other very early engineering programs, even pre-software. So there's a lot of history there, really. This is some work that a colleague and I did 2003. This is when we did a project and we looked at extreme programming. And we looked at what we were doing with, in quotes, formal methods and verification. And actually, they seemed to be quite compatible. So we wrote about that, and that's 12 years ago. Moving forwards, this is a very good book about lean. The lean software community have done a lot of very interesting work. About 20 years ago, Lockheed Martin ran one of the most effective and leanest software engineering teams I have ever seen in the world in Marietta, Georgia, building an aircraft called the C-130J, which you may have seen flying around over Wiltshire and places where it used to be based. I can't remember where they are now. Which RAF base has the C-130Js? Can't remember. But the mission computers on the C-130s were built by a team at Lockheed Martin, led by this chap, James Sutton, and they were one of the teams pioneering this idea of lean software, which was very interesting. Moving forward, formal and agile, agile and architecture. Guys at York talking about high integrity agile, so there's a first appearance of that term. If you really want the straight from the horse's mouth, no BS account of what agile is doing or not doing, this book by Bertrand Meyer is worth a look. Some of you may have seen this. Anyone read this? Show of hands. No? Oh, you should all have a look. It's mercifully short. It's only about 100 pages. And this is a straight talking, no holds barred account of what Bertrand thinks about the agile community and their practices. It's very straight talking. He says stuff's junk when he thinks it's not good, and he says some of it is inspired and brilliant, and it's worth a read because he doesn't want to sell you anything. Bertrand Meyer is not an agilist kind of person. He's just a professor of software engineering in Zurich. He's the guy behind Eiffel and all that other stuff. So that's worth a go. Okay. So moving quickly on, some of the issues, the bits where I go, hang on, that's not going to work for high integrity. So firstly, there's this kind of implicit assumption in a lot of the agile literature that there's this big emphasis on test, test, test. They talk about test first or test-driven development. And that's great. I wholly support that approach. I think it's a very, very mature way of doing business in building software. But there's this implication that there's this magic thing that when all the tests pass, you know, you've got this ever-growing body of regression tests, and when all the tests pass, that defines that everything is fine. You can ship your system, or your refactoring is done, or something. They talk about this definition of done. So this idea that when all the tests pass, everything is okay and you can ship the product. Well, is that really good enough? In the world of safety critical computing, we've known that that's not good enough for 20 or 30 years. If someone comes to me and says my system is safe, or God forbid worse, if someone says my software is secure because, in quotes, we've tested it lots, that immediately sets alarm bells ringing in my head, because such statements based upon some notion of volume of testing are usually fatuous. In particular, to claim ultra reliability, so for the sort of reliability we need for civil avionics or nuclear control systems, there is no statistically defensible way of testing a system long enough to claim the kind of reliability metrics that we need. You may have heard of this figure of, you know, a probability of on-demand failure of 10 to the minus 9 or something per, you know, for continuous control systems, 10 to the minus 9 per operational hour or something. 10 to the 9 hours is 114,000 years. Which begs the question, how much testing are you going to do to support that argument? And clearly it's fatuous. Even in the mathematics, you go back to Ricky Butler's work or Bev Littlewood's work from City University 20 years ago, the mathematics is well established. It just doesn't make sense to claim this. Even worse, claiming security properties by saying we've done lots of testing is a total waste of time, basically. We know this does not work. The OpenSSL libraries were tested by millions of people, millions of times a day, and yet that Heartbleed bug was there for how many years before anyone noticed it. It may well defy formal methods. You know, there were some people saying, oh, we could have found that. Some saying, oh, we would have missed it. It certainly defined code reviewing, that kind of bug, this many eyes theory, that, oh, if you've got enough people, someone will spot all the bugs. That's junk as well. The open source many eyes theory for code quality, I just don't believe either, because bugs like that defy the depth of the human brain, I'm afraid.
Analysis on a very cheap tool would have picked that up.
Yeah, now computers are good at some of that stuff. We'll come on to that, Chris.
The reason it would have picked it up was it was a one-line if statement, and the second go-to was indented. It would have picked up the second go-to as a suspicious indent.
Some basic discipline might have picked it up with some automation. So
you know,
it's a funny thing.
That's how it would have picked that one up.
The Apple go-to fail bug was similar. A simple discipline would have picked that up in automated analysis. Anyway, so security is even worse than safety in some regards, because we're programming Satan. Have you heard this term, programming Satan's computer? This was coined by Ross Anderson in Cambridge. It means in building secure systems, you have to assume the computer's going to go wrong in the worst possible, most malicious, most intelligent way at the wrong time when you're least expecting it. Programming a computer on that assumption is really hard because you just can't make assumptions about what does or doesn't work at any particular time. So this problem about regression test and verification, what about all the other sorts of verification we're used to doing? Personal reviewing is still very powerful, you should be doing that. Peer reviews, good stuff. As Chris said, automated static analysis is very, very powerful these days. All sorts of useful things can be done. Structural coverage we're used to, then traceability, performance, non-functional testing, all these different sorts of verification. Well, where do they fit in an agile process? They must fit somewhere, and we know we can do better. For many years we've been promoting the use of what I would call sound static analysis. What that means is static analysis that always finds all the bugs. So would you buy a static analysis tool that says, I've done my best and I found most of the bugs? Or would you buy a tool that says, there are definitely no bugs for a particular bug that you were interested in? Well, we're interested in the latter type of static analysis, and that is actually possible technically to achieve if you've got the discipline to do it, and we've done that quite successfully on a few projects. Another problem is this issue of upfront. The Agile community tend to eschew or try and at least minimise the upfront activities of requirements engineering and design and so on. You'll hear this idea of minimising design and refactoring. But in the world of high integrity, we have very demanding requirements for non-functional things like safety properties, security properties, reliability in the face of a malicious environment. So if you're building a satellite or a system that's going into space, you have amazing requirements for reliability because you can't go up and fix it. Our principal weapon for addressing these kinds of problems is what we would call architecture. So things like the physical structure and arrangement of systems. How many computers do we have? Do we have one? Do we have two with some sort of backup arrangement? Do you have 3 or 4 and they're voting? You know, just things like this. For security, we may choose to have more than one physical network with different types of data on different networks. This kind of stuff is architectural. And what seems to me a blindingly obvious observation is that we can't afford to refactor architecture. You can't build an aeroplane with one engine and say, yeah, if we need more engines, we'll refactor them in later. You know, that's just not going to work. And guess what? To build a commercial aeroplane, you need at least 2 engines. Who's ever flown on an aeroplane with only 1 engine? I hope none of you. You have, because you're in the military. If you've been in the military, if you've jumped out of an aircraft, maybe you've flown on a little plane with 1 engine, but all commercial airliners, you'll know, always have 2 engines or more. There's a good reason for that. That kind of redundancy needs to be designed in early in a system. So this idea that we could refactor architecture just does not make sense to me at all. So the idea is we need enough upfront work to get the architecture right so that we can get the non-functional stuff without invoking horrendous pain later on. How do we know how to get that right? Well, it's obvious. You do requirements engineering or you do safety engineering. Safety engineering is a pretty well-established discipline, particularly from the railway industry. The railway guys have been doing safety engineering for over 100 years. They know how this stuff works. The nuclear industry has been doing it for at least 50 years. Or you do security engineering. You look at threats and hazards and you do your HazOps and your fault trees and threat trees or whatever, and you get this stuff right up front, which requires some work and thinking, but that's just the way it goes. Another issue for embedded systems, the Agile community seems to depend upon the plentiful availability of target hardware, meaning there's a system you can test on and it's almost infinitely fast, so that you can run your regression tests in 5 minutes. The idea is that you can press a button, everything gets tested, and in 5 minutes you get your results back and you get a big tick saying everything's great. Well, that's great if you've got a sort of infinite supply of hardware and resources available, which is good for people building web servers and stuff. If you've got the Amazon cloud services available and you can fire up 100 machines to do your testing out there in the cloud, that's fantastic. For us building embedded systems, most of the time we don't even have any target hardware at all because it's not been built yet. It's a truism of our industry. The hardware is always late. You haven't even got it to test on. So what can we do to make this better? I mean, some test activities, maybe some stuff like structural coverage, you've got to do that on the target. So how can you do that if you haven't got a target to test on? So getting rid of that bottleneck can be a bit of an issue. One particular thing that may be very useful that we've been looking at recently is virtualization. So can we bring up virtual target machines? As opposed to bringing up a Linux machine or a Windows machine as a virtual platform, can we bring up a simulation of our embedded target as a virtual machine? There are tools like Cynix, some of you may have come across. QEMU is a more openly available thing. And then you've got these integration platforms like Jenkins, you've got configuration management tools like Puppet. Could we sort of leverage all that technology from the web community to bring up virtualized target rigs and simulate them, but then bring up 100 of them to do testing on or do analysis and that kind of thing? That seems really quite advantageous and potentially very useful. The other thing that's obvious is maybe we shouldn't be doing so much testing at all, and we should be doing more verification statically, which is something we've been pushing since, well, the early days of Eurofighter Typhoon, probably 25 years ago. We worked out that static analysis was a good idea, and we've been doing it ever since. So the more you can do statically, the better, as far as we're concerned. And that fits very much with the Agile approach. So to talk about the blind spots, one of the big dials we can turn up is static verification, no doubt. We find it complements test. It does not replace it. People often say to us, oh, can you do all this static stuff? And we're not suggesting removing testing at all completely. That's absolutely not the case. But it certainly complements test in some very interesting ways. It's potentially much faster if you've got the discipline to do it right. It's what I would call sounder, meaning we find more of the bugs more of the time by using strong static analysis tools. And the tools are getting very, very strong these days. Given Moore's law and the kind of computing resource we can deploy, it's incredible what the tools can do now. Under the hood of these tools now, you'll find state-of-the-art theorem-proving engines, satisfaction-solving, model-checking engines. They are amazing at what they can discover. Even about crappily written, really rubbish code, they can discover amazing things. If you're bothered to write the code really well and design it properly, you get another order of magnitude performance gain out of the tools. The tools do much better if you design your code properly. That shouldn't be a big surprise. So instead of regression test, well, how about we do regression test, but we precede that with regression proof? Well, we do that right now. Every single day we have projects at Altran that are doing literally regression proof on software. If that fails, we don't even bother doing the testing because it's just a waste of time. If the proof says no, there's a bug, we don't do the testing and we get a much quicker turnaround. The developers do this all the time. The developers do this before they commit the software into the CM system. So this is now at pre-commit phase, what the Agile or the DevOps people would call pre-commit phase of the pipeline. They don't even commit the change to the CM system until the theorem prover has run over the code and said, yep, you haven't screwed up, or something like that. On a big project, for example, the IFACS software, which is running part of the aerospace, the air traffic control infrastructure of the UK, is a bunch of stuff that we wrote. The project called IFACS, that's about 250,000 lines of code. We can reprove that from scratch in 15 minutes. So that's a coffee break to one of our developers. So they just press the button, go get coffee, come back, and if it's a small change, it might be 1 minute. To reprove the whole system, worst case, about 15 minutes now. On commodity hardware. That's not a big expensive supercomputer. So this is really cool now, because the developers just do this all the time. And surely we can do that as part of what the Agile people would call a deployment pipeline, basically, and that's indeed what we're doing. Okay, so those are some of the issues and the blind spots. Not all of them. I haven't got enough time to tell you what all the issues and the blind spots are, but that's a little sample of some of the things we've come across. The $64 million question then is, how much upfront is just right? How much work upfront, how much requirements engineering and design and architecture should you do before you start going agile and you go into an iterative pipeline style of development? By the way, all of our projects, no matter how well planned they've been, no matter how hard we try, all our projects become iterative in development and deployment. I have never done a single iteration software development project. This criticism of waterfall as this sort of single iteration process is completely bogus. No one does single iteration waterfall in the world. All our projects are iterative, so you might as well plan to do it, because you will anyway. So the question is, how much upfront should you do before going into an iterative style, I suppose? That's the important question. Well, I said that's the question and I don't know the answer. The answer is, well, it depends. It depends on sort out your non-functional properties, sort out what really matters, sort out the uncertainty. You know, what don't you know? What can you afford to defer is an important lesson we've learned from the lean engineering people, is when you can defer design decisions in a way that's appropriate is a very important thing. But watch out for this non-functional stuff. Safety and security will come back and get you if you don't think about it up front and try and get it right. That's a very brief tour of what I've been up to. I hope that's been sort of interesting. In terms of next steps, what we're looking at next is, well, what happens if we take the agile stuff, the stuff from the DevOps and the continuous development, continuous deployment communities, the ideas from the lean software community, the formal methods. I haven't said the F word today, I've now said it once. The F word is formal, which we do that as well on projects, and formal methods is good for you. It just means mathematics, and that's not something we should be afraid of. There's something called the team software process that comes from the SEI in the States that's really, really good. It's a discipline for how to behave as an engineer. What if we take all of those things and sort of mash them together and try and pull the best process out of that? That's what we're trying to deploy on the next generation of projects for us. I would urge you, please publish data. There's far too much opinion and talk in this business, not enough data. I would like to see people publish more stuff with numbers attached, rather than people just going on about their opinion. Are there any questions?
Are there any specific agile methods that seem to suit this kind of work? I mean, because there's a lot of, within the agile community itself, there's people arguing and toss over about whether Scrum is best or some other flavour of it, or is it something where really the lesson we learn from this is more about using formal techniques and continuous integration?
I think the answer is probably at this point insufficient data. There's just not enough control. It's hard to get data for these things, let alone control experiments that are worth, you know, talking about. I simply probably at this point say we just don't know enough data. We would probably, if we were going to set this up again, start with a sort of lean stroke formal Scrum mashup to start with, if only because Scrum is a reasonably well-defined starting point, and then we'd adapt from there. XP's got some good ideas in it. We'd probably adopt what we like from XP as well. I don't think any one thing is the right thing. I think you should pick what's best, measure it, work out what works for you. I know what Watts Humphrey would have said. Watts would have said measure it and work it out for yourself. If it doesn't work, discard it. If it does work, keep it.
And just one other one. Are there any lessons to be learned from the hardware development community? And you look at the sort of agile SOC people, they've been looking at, so again, a bit of some convergent evolution, you know, using formal, because formal verification is much common in SOC. I
think if there's one lesson we can learn from the hardware community, is that they were 20 years ahead of us in learning the value of static verification, because the hardware community 20 years ago learned what it cost them to tape out a faulty silicon design and, you know, go and fab it. That costs you $1 million or something. The hardware community are a decade ahead of us in terms of formal methods and formal verification in a slightly different problem domain. They're verifying circuits rather than sequential software. But you look at the use of equivalence checking and refinement checking in hardware design, it's staggering what they do. You know, I've been to Intel Labs in Portland and places, and the formal methods research team there is almost an embarrassment to me, because we don't deploy that in software. Why not? I don't know. It's irrational to me. No, we've done it for 20 years. Yeah. Look at IFAX, look at Sholis, look at CDIS. We've done projects. The company that used to be called Praxis, which is now called Altran, has been doing this for 20 years and publishing the data. So why do other people think it's difficult or impossible or beyond them? I just don't get it. There are plenty of success stories of people getting this to work. The economic incentive scheme is really odd for software engineering, meaning there's lots of good practice out there and good disciplines. So why aren't they being adopted? That is basically all I really brought for you to say.